Assalamualaikum and hello everyone. Alright, today our group will present the title of Methane Conversion over Artificial Photocatalysts in subject Chemistry of Petrochemical Processes. Okay, let me introduce our group members. First, Haziq Izzudin bin Zainal, metric number 05DPE20F2001. Second, Ioulous Ceaser anak Glennon, matrix number 05DPE20F2007. And me, Siti Sha Amera binti Ahmad, matrix number 05DPE20F2031. Hello, my name is Siti Sha Amera binti Ahmad, matrix number 05DPE20F2031. Alright, let me tell you guys the introduction of this topic. Methane conversion into value-added chemicals such as alkanes, alcohols, and other hydrocarbons represents an enduring, attractive, yet challenging topic in response to the global energy and environment crisis. Conventional thermocatalytic methane conversion suffers from harsh reaction conditions and intense energy consumption to push forward such transformation. In contrast, photocatalytic technology, featuring clean energy input, low energy consumption, and unique reaction route, has shined light on the road to conversion of methane. In this review, we present a concise overview of the typical photocatalytic processes for methane conversion over artificial photocatalysts, mainly including the non-oxidative coupling of methane, methane dry gas reforming, the partial oxidation of methane, and methylation reaction. In this particular part, we discuss their performance in different reaction systems from the aspects of reaction, mechanism, and catalyst design, aiming to acquire in-depth understanding of the light-driven methane conversion. Finally, the current challenges and future perspective in this promising frontier of photocatalyst methane conversion are presented. Okay, this is our block flow diagram for non-oxidative coupling of methane. Then this is block flow diagram for methane dry gas reforming. Then process flow diagram for partial oxidation of methane. And this is chemical reaction for methylation reaction.
Hi, my name is Ioulous Ceaser. I'm from DPE2B and my matrix number is 05 DPE20F2007. The development of high-efficiency catalysts and systems for photocatalytic methane conversion under ambient conditions is of great significance to the research of small molecule-based energy conversion and the reduction of the greenhouse effect. Historically, the initial investigations for photocatalytic conversion of methane are carried out in a static system under deep ultraviolet irradiation, which then has gradually developed into a mobile phase under visible light. In this part, developments and challenges in different types of photocatalytic methane conversion in gas phase, water phase, and organic phase reaction system will be introduced in detail. Furthermore, we will discuss different types of reaction systems based on the direct and indirect activation mechanism of photocatalytic methane conversion, hoping to provide a deeper understanding in this field. In this section, gas phase photocatalytic methane conversion following different reaction paths, including non-oxidative coupling of methane (NOCM), oxidation of methane with O2 or water vapor, and conversion of methane with CO2, or known as methane dry gas reforming (MDR), will be discussed. First research on photocatalytic NOCM was reported by Yoshida Group over several silica and alumina supported oxides under UV light irradiation. CH3 was produced over excited active metal oxygen species on the surface of photocatalysts, which then coupled each other to generate ethane, and hydrogen atoms transferred from methane captured photo-generated electrons to form H2, accomplishing the NOCM reaction. It has been found that the sample with low metal oxides loadings exhibited higher performance for the NOCM reaction to produce both ethane and hydrogen with compared to that with medium and high loadings, which implied that the creation of highly dispersed metal species were crucial to obtain high activity. However, this reaction system suffered from low conversion efficiency caused by the poor light response and serious charge carrier recombination of catalysts, and the high energy input of far UV light had unexpectedly threatened the stability. Researches on photocatalytic NOCM were further developed by Chen and co-workers, who discovered that Ga3+ modified titanosilicate zeolites were effective in photocatalytic NOCM reaction with a conversion rate of about 29.8 micromole gram -1 and H -1 after UV light irradiation for 5. The improved activity was ascribed to the synergistic effect between Ga3+ anchored sites and oxygen-centered active sites on the quantum-confined semiconducting titanate wires, in which inert C H bond was pre-weakened by the strong adsorbing ability of Ga3+ when Ga ETS 10 and 0.2 was exposed to UV light irradiation. The photo-generated holes were captured by the surface OH groups connected on the titanate wires to produce OH. The OH abstract a H atom from pre-activated methane to form CH3, which then combine with each other to release as ethane, whereas the photo-generated electrons were trapped at the Ti4+ sites of titanate wires to form reduced Ti3+ species, as evidenced by the in-site infrared spectroscopy and electron paramagnetic resonance (EPR) analysis. As a result, catalysts must be recovered through thermal treatments to eliminate the accumulated reduced species. This system provided an advisable synergistic way for pre-weakening the CH bond in methane for improved photo-driven NOCM. And this is our non-oxidative coupling of methane charts. New advances on photocatalytic NOCM reaction had been further developed based on a multifunctional catalyst and reaction systems design logic. For example, a coupling strategy of the surface plasmon resonance SPR effect of AU and the surface polarization effect of ZNO was fabricated by long group, which resulted in a stoichiometric conversion rate under simulated solar light irradiation. Besides, activities in visible light irradiation were also found. The authors proposed that methane was adsorbed on the electron-poor Zn site of the strong polarization Zn single bond plane with a bridge model to generate a 4-membered ring transition state, and then directly oxidized by the hole to form Zn single bond CH3 species, which finally undergone a coupling reaction to produce C2H6. While the H+ intermediates on the O side of the Zn single bond plane were reduced by the AU SPR field managed hot electrons to form H2. HUETAL designed a novel reaction system that consists of a continuous flow reactor and metal-loaded TiO2 photocatalysts loaded on the light diffuse reflection surface of frosted glass for photocatalytic NOCM reaction. It was found that the fluid gas atmosphere and enlarged light absorption contributed to the conversion a lot. As a result, the yield of C2H6 reached the highest reported value of 81.7 micromole over optimized AU over TiO2 with a selectivity higher than 95% under simulated sunlight irradiation and ambient conditions. This is our photocatalytic NOCM chart for ZNO and AU. Notably, it can be clearly seen that the photocatalytic NOCM reactions Systems get improved continuously, where the light source expands from ultraviolet region to visible region. The reactive sites on catalysts have a disposition to be highly dispersed and metanophilic, and the operation environment updates from static to dynamic. This also provides a more systematic and enlightening paradigm for the rational design of other types of solar-driven methane conversion.
Hi, my name is Haziq Izzudin bin Zainal. My number metric is 05DPE20F2001. For our conclusion, in this review, we have represent a concise overview of the typical photocatalytic process for methane conversion over semiconductor-based photocatalysts, mainly including the non-oxidative coupling of methane, the methane dry gas reforming, the partial oxidation of methane, and methylation reaction. In particular, dedicated emphasis is put on elucidating reaction mechanism and catalyst design with regard to their performance in different reaction systems, aiming to acquire in-depth understanding of the light drive methane conversion. So this is our reference. So if you want more detail or more info about our topic, you can go through this link.